Hello everyone, welcome back to Z Physics. Today we're going to be going over the 2018 Unified Physics paper from OCR Physics A. Okay, well, let's get started with question 1. We have the following relationship: R is equal to R naught 1 plus K theta, where R naught is the resistance of the wire at 0 degrees and K is a constant for the wire. You have a circuit up here, which we have an ammeter and a voltmeter. Additionally, we're applying some heat into this water bath over here, and what we need to do is describe how we would carry out an experiment. So remember, as always for the 6 markers, I'm just going to underline some of the things that I'm being asked to do. So I need to describe how I would carry out this experiment, how I would analyze the data to verify this relationship. In my description, I should state any precautions and as well using them to improve both the accuracy and the precision of the measurements. Okay, let's get started. So in terms of our description, we're going to be varying the temperature theta, which will be happening naturally as you place the water over the source of heat, which is going to be heating up, and then we're going to be measuring the corresponding changes in the current with the ammeter and the volt in the potential difference with a voltmeter. We're going to be measuring the temperature, of course, with a thermometer, and just to be absolutely certain we're going to get full marks, I'm just going to be as detailed as possible. So I'm saying that I'll be measuring theta with a thermometer. Now, once we have corresponding values of V and I for different temperatures, we're going to calculate the resistance using R is equal to V over I for different temperatures. Now, when that's the case, we're going to have values of R and values of theta. Now, what I'm going to do, and this will be part of my analysis section, would be to plot a graph of resistance on the y-axis against temperature on the x-axis. Now we can work to just expand this equation that we're asked to verify with an experiment, and what I'm going to do is I'm just going to expand the brackets. So I'm going to say that R is equal to R naught plus R naught K theta. Now we can rewrite this once again, and all I'm going to do is say that R is R naught K theta plus R naught, exactly like this. So just swap these around, and just underneath I'm going to write Y is equal to mx plus C. Now we can see that R is on the y-axis. We can see that theta, the temperature, is on the x-axis, so R naught times K will be left for our gradient, and our intercept C will be equal to R naught, and our gradient M is going to equal R naught times K. We can even find the constant K if we wanted to. K will be equal to M over R naught, where M is the gradient, and C can be just found by extrapolation on the graph. So I'm just going to make a little note over here that this over here is my intercept, and this intercept can be found by extrapolating. Additionally, what we also need to do is comment on both the accuracy and the precision of this experiment. So let's start off with the accuracy. And in general, when we are using water baths, there are 2 things that we need to do. One of those things would be to ensure that we are stirring this liquid constantly to allow for thermal equilibrium, and additionally we need to allow some time for this thermal equilibrium to actually set in, because it takes some time for the heat to be distributed, let's say from this part of the water bath to the upper parts of the water bath, or more importantly over here where the thermometer is. All we need to do now is to comment on the precision. As you can see, we've written over here that for the accuracy, we're going to continuously stir the water and allow time for the water to reach thermal equilibrium. For the precision, so let's just write down precision. Because this appears to be an analog thermometer, what I'm going to write down is that we need to ensure that we're not introducing a parallax error, so we need to be eye level. And let's just write down ensure measurements of theta, measurements of theta are performed from eye level. This will ensure that we don't have a random or systematic, depending on the position which we take measurements from. So we're going to ensure that they're all done from eye level. Now, additionally, I would also say that we need to consider using a device with a smaller scale division. So if we use a thermometer with a smaller scale division, this is one guaranteed way of always improving the precision of an instrument. So consider using a thermometer with a smaller scale division. Okay, folks, so just a quick check. I've described how to carry the experiment. I've described how to analyze the data, and also I've described how to determine a value for K. So K is your gradient divided by R naught. Just to be absolutely clear and make the job of the examiner as easy as possible, I'm just going to make a little footnote here that M is the gradient, just in case. M is the gradient, so K, the constant, will be my gradient divided by R naught, where R naught can be found by extrapolating. I've commented on the accuracy and I've commented on the precision. Okay, so we're good to go to the next question. Okay, folks, so part B, a student is investing a 231 kilowatt heating element, and we have quite a lot of information about the length of the wire and the diameter, etc. The first part of this question, though, is just simply asking us, show that the resistance of this nichrome wire on the ceramic cylinder is 53 ohms. Now, notice that the information this question starts off with is gives us the potential difference and it gives us the power. Now we know probably still from our GCSEs that power is equal to potential difference squared divided by the resistance. Now just rearranging for the resistance, we get that R is going to be V squared divided by the power. Our potential difference was 230 volts, so we're going to square that. We're not going to forget the square. And our power is 1 kilowatt, so I'm going to make sure that I write 1,000 here, or 10 to the power 3. And if I divide those two quantities in my scientific calculator, I am going to get 52.9, which up to two significant figures is equal to 53 ohms. Okay, next part, show that the length of the wire wound on the heating element is 5.3 meters. So we just have to imagine that there's wire and it goes around in circles all the way across there. So we're going to have a number of essentially circumferences along this heating element. So what is actually happening is you're taking a wire and you're winding it again and again and again and again and again and again. And the first thing we need to do is just figure out how many times or how many turns there are in the wire. Now we're given that the length is equal to 18 centimeters. So it's 18 centimeters, 18 times 10 to the power minus 2, what's happened there, 18 times 10 to the power minus 2. And we're given that the distance between the centers of adjacent turns, so this whole distance is sort of 18 centimeters, but the distance between adjacent turns is 1.5 millimeters. So our number of turns, let's call it n, that's going to equal 18 times 10 to the power minus 2 divided by 1.5 millimeters. 1.5 times 10 to the power minus 3. Put that into a calculator, we're going to get 120 turns. So 120 turns. Now all we need to do is just find the circumference of one of those circles and then multiply that by 120. So the circumference of one circle is equal to pi d, and what we're going to need to do is just multiply this by essentially 120, so it's going to be equal to 120 times pi times our diameter, which is 1.4 centimeters, 1.4 times 10 to the power minus 2. And as if by magic, when we put that into a calculator, we are going to get 5.28, which up to two significant figures is approximately equal to 5.3 meters. Okay, on to part 3. Okay, part 3, use the information in 1 and 2 to determine the SWG number of the Y used in the heating element. Okay, so this is really important. We're going to need to use what we've determined in part 1, which is the resistance, and part 2, which was the length of the wire. Now, the only formula that connects these quantities that we know of is the resistivity equation. So I'm just going to write this down. It's given you a formula booklet that resistance is proportional to the resistivity, which is also given in our information over here, multiplied by the length divided by the cross-sectional area. So what we can do, we don't know the cross-sectional area of this y, and this will be crucial to determining the SWG number of the following number of the following wire. So what I'm going to do is just simply rearrange for the area. The area will be equal to rho L divided by my resistance, and now I can input some numbers in. My resistivity is equal to 1.1 times 10 to the power minus 6. My length of the wire is equal to 5.3. I'm just going to put in 5.28 just to avoid any rounding errors. Then at the end I'm going to change back to two significant figures, and I'm going to divide that by the resistance, which is equal to 52.9. And the answer is 1.097, or up to two significant figures or up to three significant figures, excuse me, would be 1.01 times 10 to the power of minus 7 meters squared. So this corresponds to this number, which is also equal to 0.11 times 10 to the power of minus 6 meters squared over here. So that means that the SWG number is equal to 28. Okay, well, let's have a look at question 2. Okay guys, question 2, which is about the Taipei 101, which used to be one of the tallest buildings in the world. That building has a massive damping system, which essentially involves this weight, which is allowed to swing to side, and that acts as a shock absorber. We want to calculate the maximum displacement of this sphere in the strongest of winds, and we know that in the strongest of wind, the natural frequency of the oscillation tower is 0.15 Hertz, and we're given the maximum acceleration. Okay, well, because we're given the maximum acceleration, let's start off with writing our value for our equation for acceleration in superharmonic motion, which is that A is minus omega squared times x. Now, what we're going to do is, let's just rewrite this as minus 2 pi f, and then all of it squared times x. Now we've got the maximum acceleration and we're looking for the displacement, and we've got the frequency as well, so this should be a straightforward job. What I'm going to do is just simply rearrange for the displacement. X will be equal to a over minus 2 pi f, and then all of it squared. So x will be equal to our acceleration, our maximum acceleration, which is equal to 0.050, and we are going to divide this by minus 2 pi times 0.15 hertz, which is our frequency, and then all of it squared. And if we input that into a calculator, we are going to get 0.05 or minus 0.056 meters. So essentially this is our maximum amplitude. Now the sign just tells us whether the displacement is positive or negative, whether we are on this side, whether we are on this side over here. But in general, the magnitude of our maximum displacement is going to be 0.056. Okay, part B, explain why the natural frequency of the damper system must be 0.15 Hertz. This is really interesting. Now remember, it is the tower itself which is actually moving. So this is our driver in this resonance problem. So this is moving and it's causing the forced oscillation of this sphere. Now if the tower is moving at 0.15 Hertz and the natural frequency of the sphere is also 0.15 Hertz, resonance will occur. This means that the sphere will be moving at its largest amplitude, and this means that it will be most effective as a dampener because more energy will be transferred into this motion and away from other potentially dangerous or unpleasant effects in the swaying of this tower. Okay, so let's write this up. So what I've written this up is that the tower provides the driving frequency to the sphere, and at 0.15 Hertz, the natural frequency of the sphere matches the driving frequency of the tower. Resonance occurs at that point, so maximum energy is transferred from the tower to the sphere. Okay, part C, the acceleration of the sphere is given by the following equation. A is equal to minus k over m times x. We're given the mass of the sphere is 6.6 times 10 to the power of 5 kg. That is a very heavy sphere. Show that the force constant k of the spring is about 6 times 10 to the power of 5. Okay, well, the first thing we need to do is just rearrange for the force constant k, the above equation, which is going to give us minus ma divided by x. Now this is going to equal to minus our mass, which is 6.6 times 10 to the power of 5. Now our maximum acceleration was given in the previous question, or in the previous part of the question, as 0.05. So we're going to multiply this by 0.05 meters per second squared, and the value for our displacement, our maximum displacement, is minus 0.056 as we previously found. And if we input this into a calculator, we are going to get 5.89 times 10 to the 5 newtons per meter, which is approximately equal to 6 times 10 to the 5 newtons per meter as required. Okay, let's have a look at C part 2. So the S wave of an earthquake. Oh wow, this question now turns into an earthquake. What a roller coaster. causes a sudden movement of the building, displacing the sphere 0.71 from its equilibrium position relative to the building. Use your answer to calculate the energy transferred to the spring of the damper system. Okay, so essentially we are assuming now that the building acts like a gigantic spring. Now the formula for calculating the energy in a spring system is the energy is equal to a half k x squared, where k is the force constant or the spring constant and x is the displacement. So this is going to equal to a half times our value of k, which was 5.89 times 10 to the power of 5 multiplied by the displacement squared, which is 0.71. I'm going to be quite careful not to miss out the square because this is one of the most common errors. And if we were to put this into a scientific calculator, we are going to get 148,457 joules, and let's just put this up to two significant figures. So this is going to be 1.5 times 10 to the power of 5 joules. Okay guys, so question 3, we have a binary star system. Explain why the stars of equal mass must be diametrically opposite as they travel in the circular orbit. Now the key idea here is that they're traveling in a circular orbit, and if they're traveling in a circular orbit, they experience a centripetal force, which in this case is provided by the gravitational force. And this force is actually pointing towards the center, and it's acting essentially along the diameter of this binary star system. So 1 mark for the statement normally and 1 mark for the other. Let's have a look at part 2. The centers of the two stars are separated by a distance of 2r, which is equal to 3.6 times 10 to the power of 10. I've underlined this here because we're not given r, we're given 2r, and the stars have an orbital period t of 20.5 days. We're going to need to make sure to convert that in seconds in a minute. The mass of each star is given by the following equation over here. We've got some cubes and squares, and calculate the mass of each star in terms of the solar masses. Okay, well, let's get started. So the equation is already rearranged, so I can just write down that the mass of each star will be equal to 16 times pi squared times r cubed. Now 2r is 3.6 times 10 to the 10, so I'm going to need to divide that by 2. So bracket 3.6 times 10 to the power of 10, that is divided by 2, and then I'm going to be cubing this whole expression, and then I'm going to need to divide by g, the gravitational constant, which is equal to 6.67 times 10 to the power of minus 11 times the time period squared. Now this is given in days, so let's convert that to seconds. I'm putting a bracket here, not to forget to square it right at the end. So 20.5 days, each of them has 24 hours, each of them has 60 minutes, and each of those has 60 seconds, and that is squared. If we input that into a calculator, we are going to get 4.4 times 10 to the power of 30 kilograms. And if we divide that by 2 times 10 to the 30, I'm just going to write this over here for completion. So 4.4 times 10 to the power of 30 divided by the mass of the sun, which is 2.0 times 10 to the power of 30. This is going to give us a final answer of 2.2 solar masses, like so. So I'm just going to write this over here as 2.2 solar masses. Okay, part 3, the stars are viewed from Earth in the plane of rotation. and the stars observed using light that has wavelength of 656 nanometers in the lab. Calculate the maximum change in the observed wavelength of this light from the orbiting stars. Give your answer in nanometers. Okay, well, in order to find delta lambda, we're going to be using Doppler's shift formula. So delta lambda over lambda is equal to v over the speed of light. Now we know that this is the wavelength observed in the lab, so it's going to be 656. We know the speed of light, so all we need to do is figure out their recession velocity. Now, as the stars are moving along in their orbit, they will be blue shifted and red shifted depending where the Earth is and whether they're moving away or towards the Earth as they are orbiting. So the speed of rotation will be serving as an equivalent of essentially the recession velocity v. So we can calculate that as simply using the equation that v is going to be the circumference, which is 2 pi r divided by the time period. So let's do that. So it's going to be 2 pi times the radius of rotation. So it's going to be 3.6 times 10 to the 10. We're going to divide this by 2, which is going to give us 1.8 times 10 to the power of 10. And the time period was 20.5 days. It's going to be 20.5 times 24 times 3 times 60 times 60, like so. And this is going to give us an answer for the speed, which is up to two significant figures, 6.4 times 10 to the 4 meters per second. So now we are ready to rearrange this equation for the change in wavelength. Okay, so I'm just going to take that equation, I'm going to rearrange that for delta lambda, and delta lambda will be equal to v over c times the wavelength in the laboratory, which is going to give us our velocity is 6.4 times 10 to the power of 4. We're going to be dividing that by the speed of light, which is 3.0 times 10 to the power of 8. And because they want our answer in nanometers, I'm not going to convert that to 2 meters. So I'm just going to multiply this by 656. Like so, and if we input that into a scientific calculator, we're going to get 0.13994, and let's call that 0.14 nanometers. So that's the change in wavelength. And for part B, first of all, part B, the center of the mass of the binary star lies on the surface of the star of mass 4m. Draw on the figure 2 circles to represent the orbits of both stars. Now the ratio of the diameters of the circle is going to be approximately 1 to 4. Well, it's going to be exactly 1 to 4, and I'm trying to draw that approximately right. In an exam situation, I would really encourage you guys to use the proper drawing equipment and to make sure that you have drawn these in the correct ratio, which is 1 to 4. Now, explaining why the smaller mass star travels faster in its orbit than the large mass star, we have to imagine that they both have the same time period. This is one of the features of binary star systems, and if they both have the same time period, because the smaller one has a larger orbital distance and has a larger orbit size, then it will have to be traveling faster. So both stars have the same time period of rotation. The smaller mass star travels faster. To cover more distance. in the same time. Remember, v is equal to 2 pi r over the time period, so if the radius of your orbit increases, so will the velocity. Okay, let's move on to the next one. Okay, question 4. We have a mass which is falling down, and essentially it's pulling a cart along this line over here. Now we need to show that the following relationship v squared is equal to 1.2 mg over m plus 0.008 is true. And this looks like a complicated expression, however it's only 2 marks, so it's most likely easily derivable from energy. And additionally, I know that the formula for kinetic energy is a half mv squared, so this is probably where this factor of v squared comes from. Okay, well, let's have a go. Now, in this case, we have a conversion of gravitational potential energy to kinetic energy. So we can just write that down. So our change in gravitational potential energy, GPE, that's going to get transferred to the change in kinetic energy. Now, the only object which changes GPE is this mass m, and that falls down a distance of 0.6 meters. So the change in gravitational potential energy will be mgh, which is just mg times 0.6, and this will get transferred to kinetic energy, which is a half. Now, both of these objects will acquire some kinetic energy. So this will be the velocity of the combined system of the trolley and this mass. So the total mass is going to be m plus the mass of the trolley, which is 0.800, like so. So it's going to be half times v squared, like so. Okay, well, let's just rearrange for v squared, and we essentially have our expression. So v squared will be, if we bring the half over, that we're going to multiply the 0.6 by 2, which is going to give us 1.2 mg, and then we're going to have to divide that by m plus 0.800 as it is required. And for the next one, we needed to do a little bit of plotting. So we have a graph of v squared against m over m plus 0.800. Now this value is actually given on the previous page, and the coordinate that we need is 0.429, and 4.93 is the value of v squared, which we just calculated from before. If we were to plot this point, we would need to be very, very careful just over here, and additionally we would need to plot the absolute uncertainty. Remember, half of the size of an error bar is equal to the absolute uncertainty, so each of those lines here is equal to 0.22, and this one here is also equal to 0.22. And additionally, I've drawn my line of best fit, trying to go through as many of the points as I can. Okay, next one, use the equation given in A, which is just given over here, to show the gradient of the graph of v squared against m over m plus 0.800 is equal to 1.2 g. Okay, well, let's rewrite the above equation. So v squared is equal to 1.20 times, rather than mg, I'm just going to write gm in this case. So gm divided by m plus 0.800, like so. Let's just compare this with y equals mx plus c. So y is equal to mx plus c. I'm going to add a little plus 0 over here. So in the following equation, we can see that v squared is on the y-axis, m over m plus 0.800 is on the x-axis, uh, our intercept is equal to 0, which leaves only one thing for our gradient, and that is 120g, or 1.20g for our gradient. So our gradient is equal to 1.20 g. C part 2. Assume that the best fit straight line for data points gives 9.5 meters per second for the experimental value of g. Draw a worst fit line for the data points on figure 4.2 and determine the absolute uncertainty in the value for g. Okay, well, let's do this. So the first thing we need to do is draw the worst fit line, and if you remember, the way we draw this is we go from the bottom of the bottom error bar to the top of the top error bar. And as you can see, I've just drawn my line of worst fit. So let's figure out its gradient. In order to calculate the gradient of the line of worst fit, I've chosen a large triangle, and I've included my coordinates for which it goes. So my change in 1 will be 5.15 minus 2.25, and my change in x will be 0.43 minus 0.20. Now, if I put this into a scientific calculator, I'm going to get a value for the gradient of the line of worst fit of approximately 12.6. Now remember, in order to find the worst acceptable value for g, I'm going to need to divide that by 1.2 because the gradient is equal to 1.2g. Therefore, rearranging for the worst, for g worst, let's call it, this will be equal to our gradient, which is 12.6 divided by 1.2, and if we just divide that number by 1.2, we're going to get about 10.5 for our 10.51 for our worst acceptable fit for G. Now, in order to find the absolute uncertainty, this is going to equal to essentially the difference between the two. So G worst minus G best, which is already given over here through the line that the value of G which is found by the line which is the line of best fit is 9.5. So we'll just take them away. So the absolute uncertainty, I'm going to call that AU, is just simply equal to G best minus. Okay folks, so I've drawn a large gradient triangle in order to determine the gradient of the line of worst fit, and I've written down my coordinates over here to find my change in the y coordinate divided by the change in the x coordinate, and if I put those into a scientific calculator, I get approximately 12.61 for my gradient of the line of worst fit. Now remember, because my gradient is equal to 120g, in order to find g, I need to essentially divide my gradient by 1.2, just simply rearranging that as we looked at in the previous part of the problem. So our worst acceptable value for g, let's call that g worst, will be equal to our gradient, which is 12.61 divided by 1.2, like so. So if we input that by in a calculator, we are going to get 10.51 meters per second squared. Now in this problem we're looking for the absolute uncertainty, and the absolute uncertainty will be found by the difference between G worst and G best. Now we're given that the value of G for the line of best fit is 9.5, so all we need to do is just take away those two values, and 10.51 minus 9.5 is going to give us simply 1.1 meters per second squared. So this will be equal to plus or minus 1.1 meters per second squared. Okay guys, so part D, it is suspected the car and trolley did not pass at right angles through the light beam. Discuss without doing any calculations the effect this may have on the experimental value for the acceleration of free fall. Okay, well, if it's not passing at right angles through the light beam, then the card is going to appear shorter. And this is one thing that I've tried to visualize with my little diagram over here. When the card is striking the light beam at right angles, the apparent length is the real length, whereas if it's tilted, you're going to see that this length here is shorter than the other. In other words, we are going to get a systematic error in which the length of the card appears shorter. However, this means that it will pass quicker through the light gate, which means that the apparent speed will be higher. So each of our measurements of v is going to be of higher value. So as we said, the card will appear to have a shorter length, which means that for those data points, the measure time will be shorter, i.e. your calculated values of v and v squared will be even larger. Now, if one of those values gets shifted upwards, that means that the gradient is going to be higher. So, so we can write this in. So the gradient will be higher, and because our gradient that as we found in the previous question is equal to 1.20 times g, if our gradient increases, then our experimental value for g will also increase. So we can write this in, the experimental value for g will increase. Okay, let's have a look at question 5. So question 5, we have a rotating magnet and we have a graph of the induced EMF against time. Now explain the shape of the graph in terms of the magnetic flux linking coil. Now we can see that this is a sinusoidal graph, so in other words the EMF varies, so we can just write this down. So the EMF varies, so that means that it increases and decreases. Now the reason for that is because as the spinning magnet is rotating, so the magnetic flux is actually changing. So as the magnet spins, the magnetic flux is changing. Those two statements would get us the mark. However, just to sort of really well understand, remember magnetic flux is defined as the magnetic flux density multiplied by the cross-sectional area perpendicular to it. Now, those quantities are changing as the magnet is spinning, therefore the magnetic flux is changing, therefore the EMF is going up and it's going down. Okay, let's go through the next one. Okay guys, part 2. Now this figure shows us the variation of the EMF with respect to time. From there we need to figure out what the magnetic flux linkage will look like. Now whenever the EMF is at a maximum, we know that our magnetic flux linkage will be at its steepest. In other words, this peak here will correspond for the graph of the magnetic flux linkage passing through the origin at its steepest. It will also be a cosine curve, something like this, like so. I'm going to carefully just draw that, like so. It's just a sketch, so the actual amplitude, we don't really know this, so the amplitude is arbitrary in this case. Notice a couple of really important points though. So it crosses the x-axis, so this is the steepest point. So when the magnetic flux linkage changes most rapidly, this corresponds to a peak in the EMF. So this is another point over here, and this is another point over there. The reason why that is the case is because your induced EMF is proportional to minus your the rate of change of magnetic flux linkage, which is normally written as delta MBA divided by your change in time. If you have your mathematics hat on as well, you will quickly realize that this rate of change is actually a derivative, and you could find the magnetic flux linkage essentially by integrating the curve of the EMF, which is a sine curve, as we can see, and the derivative, the integral of that curve is a negative cosine, which will eliminate this minus sign over here. So what we should be expecting is a cosine curve. This is not on the specification. However, if you really enjoy mathematics, this is another way to verify your answer. Okay, part 3, we need to calculate the maximum magnetic flux through this coil using the following equation. I'm just going to convert this equation to mathematical symbols. So what I'm going to write is this V0 is equal to 2 pi times the frequency, which is F, times my magnetic flux linkage, which is N, times the magnetic flux phi. Now in this case, this is written in bold, which means that there's a potential for an error. It's something which we need to be watch out for. We're looking for the magnetic flux. Now the magnetic flux is this quantity phi, not the magnetic flux linkage, which is N times the magnetic flux. So let's rearrange for phi. Phi is going to equal to V0 over 2 pi F times N. Now we're ready to substitute some numbers into the equation. So our V0 is 1.2 volts. I'm going to divide it by 2 pi. The magnet is spinning at 24 times per second, which means that this is essentially its frequency. So it'll be 2 pi times 24 hertz. Because frequency is just the number of cycles per second. In this case, it does 24 cycles in a second, multiplied by n, which is the number of turns, which is 150. And if we input this into a calculator, we're going to get a value for the maximum flux, which is 5.3 times 10 to the power of minus 5, and the unit of magnetic flux is Webers. Okay guys, so let's have a look at part B. A student is given a transformer with coils X and coils Y. They're investigating how the maximum induced EMF in coil Y depends on the frequency of the alternating current in coil X. Describe how you would investigate the suggested relationship between V0 and X, and that suggested relationship is just Faraday's law that indicates that the maximum induced EMF should be directly proportional to the frequency. In your description, include all the equipment used and how you would analyze the data collected. Use the space below to draw a suitable diagram, which I've already drawn over here. Now, what we've done is we've connected an AC power supply to coil X, and this is going to have current which will be constantly changing direction. This will be changing the magnetic flux, and consequently that means that there's going to be an induced EMF in coil Y. We've connected an oscilloscope, and with the help of that oscilloscope, we'll be able to measure the time period. Remember, in general, in an oscilloscope, we have time on the y-axis against voltage on the x-axis. So we're going to be able to take those two measurements. As always, with 6 markers, I'm going to just quickly underline some of the things that I need to look at. For example, I'm going to need a description of this experiment. So I'm going to include all of the equipment which I will be using, and how I would analyze the data collected as well. Okay. Now, for our description of our experiment, I've just written over here that we're going to connect an AC power supply to X and an oscilloscope to Y. We're going to use the oscilloscope to measure the time period, and then we're going to be using that to calculate the frequency using the equation F is equal to 1 over T. We're going to vary the frequency of our power supply, which we'll be able to measure in the oscilloscope, and we're going to be measuring the corresponding change in the output voltage V. Now, in the oscilloscope, V is going to be equal to the height times the amount of volts per division, and T is going to equal the length of the cycle times the time per one division. Now, what do I mean by that? Remember, what the oscilloscope display looks like are these squares. Each of them is 1 centimeter long. However, in different setting, that one square will correspond to different amounts of voltage and different amounts of time. For instance, if one square was, let's say, 1 volt, the height of this wave would be 1, 2, 3, 4 volts. That is if one square was 1 volt. So this would be 1 volt, this would be 1 volt, this would be 1 volt. So depending on the setting, we'll need to multiply the actual height of the wave multiplied by the amount of volts per each division, and exactly the same, we're going to be measuring the length of one time period. Let's use maybe red for this one. We're going to measure the length of one time period, and we're going to multiply this by the amount of seconds or milliseconds or microseconds per one time division. Now, after we have all this data, which is essentially your output voltage and your time period, once again, I'm just going to write that we're going to just calculate the frequency. So we can just write this down. So calculate. So after we have all this data, we're just going to calculate the frequency F using F is equal to 1 over T. Now, at this point, we'll have tabulated data of the potential difference V of the induced EMF against the frequency, and this will allow us to plot a graph of V against F. Now, if that relationship is correct, if the suggested relationship is correct, and that is that they're directly proportional, the graph will be a straight line through the origin. And this concludes our analysis section. Okay, let's have a look at the next question on the paper. Okay, folks, so let's have a go at the last question of this paper, which is about a photo multiplier tube. We have quite a lot of information over here. We have an incident gamma photon, and we have some visible light as well. Now, the refractive index of the scintillator crystal for visible light is 1.69. The refractive index of air is 1. Calculate the critical angle for this crystal. Okay, well, as we know, the sine of the critical angle, so sine of C is equal to 1 over the refractive index of that substance. So this is the formula which we are given in our formula sheet. We can use the inverse sine, so C will be inverse sine of 1 over n, which is going to equal the inverse sine of 1 over 1.69, which is the refractive index for visible light. And if we put that into a calculator, we're going to get 36 degrees. Now we're going to see that visible light follows the following path. None of it is refracted, it is totally internally reflected, and this is because the angle of incidence is greater than the critical angle. So that means a total internal reflection occurs. So let's just write this. So our angle of incidence is greater than the critical angle, is greater than the and that means that total internal reflection occurs. Okay, so part B, high energy gamma photons passing through the scintillated crystal, converting some of its energy into visible light of wavelength 450 nanometers. Show that the energy of a single photon of wavelength 450 nanometers is less than 3 eV. So we're just going to find the energy of that photon using the good old equation that the energy is equal to hc over lambda. And this is going to equal to Planck's constant, which is 6.63 times 10 to the power of minus 34, multiplied by the speed of light, which is 3.0 times 10 to the 8. We're going to be dividing that by the wavelength, which is 450 nanometers, so 450 times 10 to the power of minus 9. And if we plug this into a calculator, we are going to get 4.42 times 10 to the power of minus 19 joules. Now remember, in order to convert this to electron volts, we will need to divide by the elementary charge. So 4.42 times 10 to the power of minus 19 over 1.6 times 10 to the power of minus 19 is going to give us 2.76 eV, which is less than 3 electron volts. Okay guys, so the photocathode is coated with potassium, which has a work function of 2.3 eV, and each photoelectron is accelerated by a potential difference of 100 volts between the photocathode and the metal plate called the first dynode. Now show that the maximum kinetic energy of an emitted electron at the photocathode is very small compared to its kinetic energy of 100 eV at the first dynode. Okay, well, we're going to have to use Einstein's equation. We know that the incoming photon of light which emits the photoelectron is 2.76 eV. So remember, Einstein's equation just says that the energy of the photon is equal to the work function plus the maximum kinetic energy of the emitted photoelectron. So that means that K max will be the energy, so let's say E photon minus the work function. Now the energy of the photon we've just calculated up here, that's 2.76 minus the work function, which is 2.3, which is going to give us 0.46 eV. Now 0.46 is significantly less than 100 eV as quoted earlier in the question, so we have shown that. Okay, and in the last part, there are 2,000 photoelectrons are released from the photocathode. Each photoelectron has enough energy to release 4 electrons. These 4 electrons are then accelerated to the next dynode where the process is repeated. There are 9 dynodes in the photomultiplier tube. The total number of electrons collected at the anode for each photoelectron is 4 to the power of 9. Okay, well, this question is just has quite a bit of information, so it's important to distill it to its very basics. Now, there are 2,000 photoelectrons are released from the from the photocathode, and then each photoelectron has enough energy to release 4 further electrons. So that means that the total number of electrons is going to be 2000 times 4 to the power of 9. So 4 times to the power of 9. Now these will be the total amount of electrons, and our total charge will be the number of electrons times the elementary charge, which is 1.6 times 10 to the power of minus 19. And if we multiply those out, we are going to get 8.4 times 10 to the power of minus 11 coulombs. Okay, if you wanted to calculate the average current, all we need to do is essentially use the formula for electric current, which is that this is the rate of flow of charge. So our charge is going to be 8.4 times 10 to the power of minus 11, and we're going to divide that by the time for this electric pulse, which is 2.5 times 10 to the power of minus 9. And if we divide those two numbers, we are going to get 0.034 amps for the current. Okay, folks, so this was the entire unified physics paper from 2018. If something doesn't make sense with these questions, please feel free to drop a comment. And thank you very much for watching, and please consider liking and subscribing this video. Thank you.